Hello children, in this lecture we will discuss imperfections or defects in solids. Okay, so what is imperfections or defects? Imperfections or defects in a crystal is the absence of the constituent particles from its regular position in the lattice, or any departure from the perfectly ordered arrangement in a crystal is termed as imperfection or defect in the crystal. Okay, so only one type of defect you are having in your syllabus, and that is point defect. So point defect are caused by a departure from the periodic arrangement of particles in the vicinity of an atom or a group of atoms are called point defects. Okay, students. So point defects or atomic imperfections arises due to deviations from ideal arrangement around a point or an atom in a crystalline substance. Okay, so point defects arises due to missing of atoms or due to the displacement of atoms or due to the presence of extra atoms in the lattice. Okay, so these are the ways due to which point defects can be arises. Okay, so the reasons are the first, due to missing of atoms, displacement of atoms, or presence of extra atom in the lattice. Okay, students. Now the type of the point defect. Point defects are classified under two headings: stoichiometric defects and non-stoichiometric defects. Okay, students. So as you can see from here, this is the detailed division of point defect. Okay, so first, point defect is having two types: stoichiometric and non-stoichiometric point defects. Okay, now stoichiometric point defects are of these four types: vacancy, interstitial, Schottky, and Frankel. These four types are of stoichiometric point defects, and non-stoichiometric point defects are of two types: metal excess defects and metal deficiency defects. These metal excess defects are divided again two types: metal excess defects due to anion vacancy and metal excess defect due to interstitial cation. Same way, metal deficiency defect is divided in two types. First is metal deficiency due to cation vacancies and metal deficiency defect due to interstitial anion. Okay, students. So again I am repeating this classification of point defect. Point defect are classified under two headings: stoichiometric and non-stoichiometric. Stoichiometric point defects are further classified in four different types: vacancy, interstitial, Schottky, and Frankel. Whereas non-stoichiometric point defects are classified under two headings: metal excess and metal deficiency defects. Metal excess is having two subtypes: metal access defect due to anion vacancies, and metal access defect due to interstitial cations. Same way, metal deficiency defect, first due to cation vacancies, and the second metal deficiency due to interstitial anion. So first is stoichiometric defects. These are the point defects which do not disturb the stoichiometry of the compound, are called stoichiometric defects or intrinsic or thermodynamic defects. Okay, students, and according to one more definition which is given here, the stoichiometric defects are the defects when the ratio of the number of positive and negative ions, that is, the stoichiometry of the crystal is not disturbed by the defects present in the crystal. Okay, so in this condition, the defect will be known as stoichiometric defects. Okay, so means equal number of units will be missing from the crystal lattice. Then this stoichiometric defect is divided in 4 types, and first is vacancy defect. So in vacancy defect, when some of the lattice sites are vacant, resulting in the decrease in the density of the substance, is called vacancy defect. Okay, and this defect may be come in existence due to the heating of the substance. So as you can see here, in this crystalline structure, these 2 units are missing. Okay, so due to the missing of these 2 units, the stoichiometry of this crystal will not be disturbed. So such defects are known as stoichiometric vacancy defect. Okay, now next is interstitial defect. These are the defect when some constituent particles that may be atoms or molecules occupy an interstitial site. The crystal is said to have interstitial defect with increase in the density of the substance. Okay, students, so in interstitial defect, the interstitial site will be occupied by some extra unit from outside. So due to this, the stoichiometry of the crystal will not disturbed, but due to the presence of extra particles or extra units, overall density of the crystal will increase. Okay, students, so the vacancy and interstitial defects are shown by non-ionic solids. But if similar type of defects are shown by ionic compounds, then these defects are known as Schottky defects and Frankel defects respectively. Okay, so Schottky defect and Frankel defects are also stoichiometric defects which are present or found in ionic substances or ionic crystals. So what are Schottky defects? Schottky defects, these are the defects which are arises when some of the lattice points in a crystal are unoccupied. Okay, so in ionic crystal, when some sites are unoccupied by their ions, then such stoichiometric defects in ionic compounds are known as Schottky defects. Okay, so as you can see here that in this defect, equal number of positive and negative ions will be missing from the lattice structure. Okay, so that is why the overall stoichiometry of this ionic substance will not disturb. Okay, students, so such type of defects are shown by halides of alkali metals like sodium chloride, potassium bromide, cesium chloride, and also by silver bromide. Okay, students. Now next is Frankel defect. This defect arises when an ion is leave its site and occupies an interstitial site. As you can see here in this diagram that one cation is missing from its original site and it is occupying interstitial site. Okay, students. So due to this effect, vacancy holes are originated and there will be no change in the density of the crystalline structure, and also dislocating ion is generally positive ion due to its smaller size, and that is why it can be easily accommodated in the interstitial space. Okay, students, so these two defects, Frankel and Schottky, are very important. So next we will discuss the differences between these two defects. Okay, now according to the points are given here. First point, Schottky defect arises when equal number of cations and anions are missing from their normal lattice sites. Okay, so in this defect, ions are leaving their site but in equal number. If one negative ion, then same one positive ion will leave its site. Okay, in Frankel defect, ion which is generally positive ion leave their lattice site and occupy interstitial site between the lattice points. Okay, so in this defect, ion is not leaving the crystalline structure. Here ions, equal number of opposite ions are leaving crystalline structure, but here ions are not leaving crystalline structure. Okay, only a dislocation is taking place inside the crystalline structure. So positive ions from their original site are occupying interstitial site. Okay, so that is why here there will be no any change in density, but in this case density will decrease. The second point, it is common in highly ionic compounds which have high coordination number and having cations and anions of almost equal size. But here in Frankel defects is found generally in those ionic compounds which possess low coordination number. Low coordination number and anions are much larger than the cations. Okay, students, when anion will be much larger than cations, that is why the interstitial site which is formed due to large sized of anions will be also large in size, and that is why positive ion will be easily accommodated in this interstitial site. Okay, students, so here the size of ions is about same, but here anion size is much larger comparatively to cations. Then third point, it decreases the density of the crystal, and here the density of the crystal will remain same. Last point, no effect on the dielectric constant of the crystal. Okay, because equal number of ions are leaving the crystalline structure, but here dielectric constant of the crystal increases because similar charges come closer in this defect. Okay, students, so these differences are very important. Then next we will discuss non-stoichiometric defect. Non-stoichiometric defects, and as I already told that these are of two types, metal excess and metal deficiency. Metal excess due to two reasons. First, due to anion vacancies, and second, due to interstitial cations. Okay, and metal deficiency is due to cation vacancies, and next due to interstitial anions. Okay, students, so non-stoichiometric defects. So as the name is indicating, due to these defects, stoichiometry of the crystalline substances get disturbed. Okay, so according to the definition which is given here, when the ratio of the number of positive and negative ions, the stoichiometry of the crystal gets disturbed by the defects present in the crystal. The defects are referred to as non-stoichiometric defects. Okay, so the first type is metal excess defect, and in metal excess defect, as the name is indicating, in these defects number of positive ions will be comparatively higher than the number of anions. Okay, so metal excess defects due to anion vacancies. First type, metal excess defect का first type due to anion vacancy, and this type of defect arises when an anion is missing from its lattice site, creating a hole, and the hole is occupied by an electron to maintain the electrical neutrality of the crystal. Okay, so as it is shown here in this diagram, this site which was occupied by an ion, and now an ion has left this site and it is out of the crystalline structure. Okay, so due to the absence of ion, the stoichiometry of this crystalline structure is disturbed now. Okay, and for neutrality of the crystalline structure, to retain the neutrality of the crystalline structure, the electron of the anion is get trapped here in this site, at the site of anion. So this site where electron is trapped is known as F center, and F stands for Farbe, which is a German word meaning color. So these F centers are the responsible for the particular color of the crystal. Okay, students, the crystals of the halides of alkali metals like potassium chloride and lithium chloride are showing metal excess defects due to anion vacancies. And as you can see from here that due to the presence of F centers, these crystals are showing particular color also. So in KCl, F centers are imparting violet color, whereas in lithium chloride, F centers are imparting pink color. The next type is metal excess defects due to interstitial cations. So in such defect, an positive ion is present in interstitial site. Okay, students. So as written here, this defect arises when an extra positive ion is present in an interstitial site. The electrical neutrality is maintained by the presence of an electron in some other interstitial site. So as you can see here in the example of this crystalline structure, here an extra anion is present here in interstitial site of the crystal, and to maintain the neutrality of the this crystalline form, this extra electron is present in somewhere else in interstitial site. Okay, students. So such type of defects are found in zinc oxide. Next is second type of non-stoichiometric defect, and that is metal deficiency defects. And in metal deficiency defects, first type is metal deficiency defects due to the cation vacancy. Okay, so as the name is indicating, metal deficiency defects. So in this defects, number of positive ions will be less in comparison to number of negative ions. Okay, and first type is due to cation vacancies. So in such defects, a positive ion is missing from its normal lattice site, and the charge is balanced by a nearby metal ion having higher positive charge or higher oxidation state. So such type of defects are found in compounds of such metals which are showing a variable oxidation state, like ferrous oxide and ferrous sulfide, nickel oxide, etc. Okay, so this is the diagrammatic representation of metal deficiency defect. As you can see here, that this site here cation is missing, and this nearby cation is carrying an extra positive charge to maintain the neutrality of this crystalline structure. Okay, students. Then second type of metal deficiency defect is due to the interstitial anion. Okay, so in such defect, an anion is present in interstitial site of the crystal, but as we all know that the size of anion is comparatively larger than positive ion always. So that is why the interstitial site will be not have such area in which this comparatively larger size anion can be occupied easily, and that is why this type of non-stoichiometric defect is generally shown by the substances. Okay, students. Next is imperfections or defects caused by impurities. So these are the defects which are due to the presence of impurities in the crystalline substance. That is why these defects are also known as impurity defects. Okay, so if a foreign atom or ion as impurity occupies a lattice site in place of host atom or ion, is called impurity defect. Okay, now The introduction of defects by the addition of a small amount of a foreign substance in the crystal of a pure substance is called doping, and the crystal containing a foreign substance as impurity is known as doped crystal. Okay, so this doping is a very important process nowadays, and with the help of this doping we are increasing the property of the related element or the compound, okay, for the different purposes. Okay, so by doping we can increase the conductivity of the particular crystalline substance. Okay, students, so the doped crystal may be regarded as solid solution. Doped crystal can be regarded as solid solution. Okay, students, it may takes place, this doping process may takes place in ionic as well as in covalent solids. Okay, students, then so first heading is introducing impurity defects in covalent solids. So how can we introduce impurities in covalent solids? Okay, so the impurities added may be electron rich or electron deficit. These are also called as electronic defects. Okay, now we can mix or we can dope the host compound or host element with electron rich impurity. Okay, for example, when group 14 elements like silicon or germanium having 4 electrons in the valence shell is doped with group 15 elements like phosphorus or arsenic having 5 electrons in their valence shell, this excess electron increases its conductivity and are called n-type semiconductor, as you can see from here. So this is the perfect silicon crystal without any impurity. Now we are mixing an electron rich impurity in this in the form of arsenic. So silicon is having 4 electron in outermost shell, whereas arsenic is having 5 electron in outermost shell. Okay, so as you can see here, this extra electron will be present with arsenic. Okay, and this electron will be in the form of mobile electron, and such electron will be responsible for the increase in the electrical conductivity of the silicon. Okay, so due to the presence of electron rich element and extra electron, so electrons are a negatively charged particle, so that is why the substance, this doped substance or doped crystal is known as n-type semiconductor. So semiconductors in which conductivity is increased due to the presence of extra negative charge in the form of electrons, such semiconductors are known as n-type semiconductors. Okay, and the second way to increase the conductivity by doping with electron deficit impurities. Okay, now again, for example, this is silicon with 4 electrons in outermost shell in the form of perfect crystal. Now when we are going to dope the silicon with aluminium, so we all know that aluminium is having 3 electrons in outermost shell only. So one hole will be found here, which will be due to the one less electron in outermost shell of the aluminium. Okay, and these hole will be responsible for the increase in the conductivity of this doped silicon with aluminium. Okay, so due to the presence of extra hole which are responsible for increased conductivity, such type of semiconductors are known as p-type semiconductor or positive semiconductors. Okay students, and same way we can introduce impurities in ionic solids also. So in case of ionic solids, the impurities are introduced by adding impurity of ions. If the impurity ions are in different oxidation state from that of the host ions, vacancies are created, which result in the higher electrical conductivity of the solid. For example, if we are mixing strontium chloride in sodium chloride, okay, then strontium ion, which is bivalent ion, will displace a sodium ion here, and to neutralize the extra charge of this strontium ion, one more sodium will be missing from its side. Okay, means each strontium ion will replace 2 sodium ions, and it will occupy just one side. One extra charge which is present here with strontium will counterbalance this neutrality of this crystalline structure. Okay students, so in this way we can mix some impurity in ionic compounds also to increase their conductivity. Okay students, thank you.